All right. So it gives me great pleasure to introduce our plenary speaker today, Professor Martin Steinbuch. Martin did his PhD actually in the wind energy area, which is an area that my research group is relatively active in now. And his PhD work has had quite an impact, and we cite his work quite often. But before he got his PhD, he was hired by Philips Laboratories, and so he moved into motion control systems. He has over 12 years of industrial experience at Philips Research Labs and Philips Center for Manufacturing Technology. He is now a distinguished university professor at Eindhoven University of Technology, where he is head of the Control Systems Technology Group of the Mechanical Engineering Department. And he also serves as director of the Automotive Systems Graduate Program at Eindhoven University of Technology. He's also the scientific director of the Center of Competence for High-Tech Systems of the Federation of Dutch Technical Universities. He's editor-in-chief of the IFAC Journal of Mechatronics, and in talking with him before the plenary, he said his research interests are primarily in motion control. If it moves, he's very interested in it. And I noticed this last night, he spent quite a bit of time in that flight simulator gallery, especially on the interactive flight simulators, seeing how many kills he could get. I was happy to see you enjoying yourself there. So please join me in welcoming Professor Martin Steinbuch.
Yes, thank you, Lucy, and also Danny for inviting me here. It's a great pleasure and honor to speak here. I have to say it's a really nice conference. We, as an audience, we don't suffer too much from the things which are playing behind the doors with respect to the organization here with the hotel. But I'm happy with the open bar this evening as a result. And indeed, the flight simulator was really great. So together with Tom Omen, he was the pilot, I was the gunner. So I experienced that we can do learning control, because the first time we killed 3, the second time 4, the third time 11, and then we switched roles. And that was stupid. So I was the pilot and he was the gunner, and then we shot only 6. And we in fact should stop because he was quite white on his face. So. But I can come home and say that I really did some control engineering learning practice again, so that was great. So I will be talking about high-tech systems, and as Lucy said, I did my PhD in wind energy, and I finished writing the booklet while I was already working at Philips. The ACC has been my conference, so to speak, from my very first start being in the scientific field. My first ACC, I still remember it was in Boston, 1985. It was my first transatlantic flight. I was 25, so I took a huge suitcase for only 5 days. Now I have just cabin luggage. I took a tie the first day. Nobody wears ties here, even not in 85, but I had a tie because I did not know yet. But it was a great conference. We had also there the workshop on model error concepts and compensation, organized by Bob Skelton and David Owens. Really interesting. It was a time of uncertainty modeling and try to find ways to actually use it in practice. So I went then to Philips, and I worked from that time basically on high-tech systems, and today I will show you the things I work on or have been working on: CD players, wafer scanners, but I will also show you the things we do on robots and on cars, because cars are in fact also robots. A little bit about engines and plasma fusion. That's my latest hobby. So I went to Philips Research, and I started to work as a researcher on CD players. At that time, the goal was to increase performance, increase bandwidth, so as to make it possible that you could make data storage with optical recording. And I had to work as a researcher, I had to work with people in the development, and there were about 15 servo engineers, tuning every day PID controllers for the radial track following and the focus track following. And I came there as a graduate. I had a PhD in wind energy, and I applied LQ optimal control, so static output feedback. I knew everything about state space models, and optimal control and Lyapunov equations, and I came there and I did not know how to tune a PID controller. And I felt really ashamed because I had a PhD in control. I could not tune a PID, and those guys could. So how could I achieve to get confidence of the development department to put my new things to them? Well, I was not able to tune a PID controller. So of course I learned, I mean, that's not that difficult, but you have to take the time for it. So since then I'm an expert in loop shaping, I could say, but more important, I already said to myself at that time, if I ever am going back to the university, the first thing I'm going to do is in the curriculum of the master students, I'm going to put classes where people really learn how to do loop shaping, or in fact how to tune industrial controllers, so that there never will be a gap anymore between what you learn and what is practice. Because I think due to this gap people forget about state space and they just go for the industrial solutions, and if you make that gap closer, then maybe our technology finds its way more easy. So that's in fact what I did, but I had a great time at Philips. I had a great time. So I learned loop shaping. Typically this is a frequency response of the radial tracking at that time. So you see a -2 slope, it's a mass, a force, no friction to the fixed world, no stiffness, so a -2 slope, the law of Newton. You see some resonances. So you apply a PID controller with an integral action and maybe some notches. If you apply H infinity, the outcome of the H infinity toolbox will also be a PID-like system with notches, of course. If you apply this to the system and you look to the spectrum of the radial track following error, you see this. So this is a linear frequency scale. This is the spectrum of the radial error. And what you see is that there are a lot of harmonics. And up to that time, the servo systems did not use that knowledge. They only had implemented a PID controller with notches for the resonances. So how stupid are you if you see this error that you don't make use of this knowledge, right? So basically what it is, this is the periodic disturbance from the disk not being eccentric, being a sort of a potato-shaped spiral on the micron level. You get higher harmonics. So the natural thing to do is to apply repetitive. Now this was back in 1987 or so, and repetitive already was invented in the 70s. There was a guy in Philips Research who implemented that in analog electronics. So it was known, but it was not used basically. And I worked on that repetitive in that time. Now it's hard to see, but this is the sensitivity, and on top of that in gray, light gray, you hardly can see it. You can see the notches in the sensitivity, which are due to the peaks in the open loop due to the repetitive controller. What you also might see, but it's difficult to see, is that in between the periodic components you amplify, in fact, and that's the water-bed effect of Bode. Now in the frequency domain, this is the result. The bottom plot is with including the repetitive controller. You get it almost for free, this performance. It leads to a much lower error. The ball game I experienced, the ball game is all about Bode sensitivity. So I like this plot very much, of the link to the Gunther Stein's Bode lecture a long time ago. This is the ball game of servo engineers. You scrap away, you get performance at low frequencies, but you have to put the dirt somewhere and it's going to hit you. The basic idea of our profession is high gain feedback. And I like to stress always this simple idea of high gain feedback. If you have a disturbance on a plant G, the open loop response is simply G times D. The closed loop response, it's from D to Y, it's the process sensitivity G over 1 plus GK for CISO. And if the gain is high, K goes to infinite, then Y is going to 0. And the benefit of feedback is the ratio between the closed loop behavior and the open loop behavior. Right, so that's the process sensitivity divided by G, which is the sensitivity function again. So the sensitivity function is the key function for performance, as well as, by the way, for stability, because the peak value is the shortest distance to the -1 point. So the key thing of feedback is the sensitivity, but this is the problem of the sensitivity, right? So you take dirt away somewhere, but you have to put it elsewhere. So what we did at Philips Research at that time was to sort of make a design cycle where you really use the knowledge of your disturbances into your design and your loop shape of your controller. And we were in fact able to do the following in 7 minutes. We could measure a frequency response, fit a model, made new weighting functions based on the error spectra of the previous cycle, do mu synthesis, model reduction, implement, measure again, look to the error spectra, and do the cycle again. In 7 minutes we could do this. This is one of the benefits of motion control. Experimentation is so cheap. You have a 10 kilohertz sampling rate normally, so in 1 second you have 10,000 data points. So this is great. And then you can really squeeze out Bode sensitivity. You can really make the spectrum of your error white. Because it's white, you can stop. So this was sort of the thing I was working on every day. How to cope Bode sensitivity. In fact, how to circumvent if possible. I will come back to that later on. And modern machinery, it can help, but it does not solve, of course, this limitation of performance. So the key things I learned from my time in Philips is plant modeling, fine. Everybody is focused on plant modeling, but disturbance modeling and specification modeling is as important as the other part. And do more with data. So make a sort of a data-based way of doing research and solutions. So then I also started to work on wafer scanners for ASML. Wafer scanners are one of the most, well, in fact it is the most brilliant motion system I know. So this is a short video. I will turn off this beautiful piano music. How chips are being made. So what you see here is silicium. They make a huge material tube of that, or not a tube, a whole pile. The diameter up to now is 12 inch, 300 millimeters, but the next phase will be 18 inch, 450 millimeters. This is the lithographic process step where you in fact make the patterns on the wafer. And you will see a close-up now how this actually works. So this is the scanning process of making this lithographic process on this wafer containing these dies to be. And this process is being done with, say, 250 wafers per hour, which is approximately 4 wafers per minute. So this is 15 seconds per wafer, and you have to scan the whole wafer. If you have done that once, you take out the wafer, you do chemical processing, you take away layers, you put substrate on it, you put it again back into the machine and do another layer, and that is repeated 20 to 40 times, and then you can make a whole structure which is becoming a chip. So 20 to 40 times the same wafer comes into the machine, and you can imagine if the accuracy is about nanometers making chips, that the accuracy of this machine is indeed also incredibly. And indeed the specifications of these wafer scanners are nowadays immense. The accuracy should be better than, say, 2 nanometers servo error, while moving at high speeds and high accelerations. So when this whole process started, and we are going back to the 70s, people in Philips research invented what they called the silicon repeater. It was basically an H gantry style of machine, so linear motors, 3 linear motors, Y1, Y2, X, and an air bearing. This still was for very small wafers. The accuracies were microns. And then 10 years or 20 years later, ASML machines are now being sold for 50 million euros. And they have stages of 100 kilo. They move with accelerations of 40 meters per second squared, 4 Gs, with speeds of 1 meter per second, with accuracies of 2 nanometer. This can only be done because these stages are incredibly well designed. They don't have friction, they don't have hysteresis, they all use Lorentz force actuators to not have contact. This is an incredible machine, and it pushes our technology also of control engineering to the far end of what we can in fact achieve. So here's the lens. It's hard to see, and you see the wafer here. This is a magnet plate. They are moving on a magnet plate. It's 6 degrees of freedom levitation, so no connection with the fixed world. There's a core stroke, and inside this box there is a short stroke, also 6 degrees of freedom. The magnets are put on the moving part of the short stroke, and the coils are on the coarse part of the short stroke, so that there's no mechanical connection with cabling. So for one stage you already have about 12 inputs and outputs. Because the forces are so high, 40 meters per second squared times, say, 100 kilos, that's 4 kilonewton, you have to apply to these machines. And the reaction forces are going to the outside world. So the whole floor is vibrating, the machine next is vibrating, the metrology system is vibrating. So what we invented in Philips Research is to make a balancing mass. So the base plate here with the magnets is moving as well, with the ratio of the masses. So the outside world does not feel any force anymore. So this is a scheme how it sort of works. It's a little bit complicated, sorry for that. It's a side view, it's a typical mechanical engineering design drawing, I would say. So on the bottom you see the base frame, then you see the magnetic layer with all the magnets, then you see the coarse stroke, and a short stroke, all Lorentz force actuators, 6 degrees of freedom. On top you see the reticle stage. The reticle stage has to move 4 times as fast because of the magnification of the lens, so 160 meters per second squared accelerations. Specs also nanometers. So you have the planar long stroke, you have the drift motors for the balancing mass, of course. Planar encoders are used nowadays. There's immersion, so there's fluid to improve the numerical aperture. And also this fluid brings in disturbances. Yeah, so everything counts here. So what's the challenge from a servo point of view? Well, this is 6x6 frequency response measurements of such a stage, 6x6. So what you can observe again is a -2 slope basically, for the mass. No friction to the fixed world. And a lot of resonances. Now the challenge is becoming, if we go from 12 inch to 18 inch, so from 300 millimeters to 450 millimeters, that these stages are becoming more heavy and heavy and heavy. And that's not possible to go on with this. So what we instead try to do is to reduce the mass of the stage, but if you do that, flexibilities come down because stiffness is lower. So we have to cope with now flexible stages in future, right? And the way we do that is to think in a more elaborate way about controlling flexible systems by adding actuators and sensors. So we have now a motion system with, say, 6 degrees of freedom, but we add actuators and sensors, say 8 inputs, 12 outputs, and then you have freedom basically to modify the flexibilities or damp the flexibilities in your structure. So we go from just single input, single output decoupled systems, we go to systems where spatial dynamics are becoming relevant. Now for that we made, or ASML made, and we can use it, a test setup, a stage. You can see here the short stroke stage, 6 degrees of freedom, but we are free there to add additional actuators and sensors. The special thing, by the way, compared to vibration control is that we do not add piezo actuators, say, to dampen vibrations. No, we sort of make the motion actuators more in number. So we have, say, 8 motion actuators doing a 6 DOF rigid body motion control problem, as well as a 2 DOF flexible mode reduction problem. So we sort of combine vibration control and motion control. Now one of the things we do is basically manipulating those additional design freedoms. So playing around with matrices in the feedback loop to cancel certain modes out of what we see as a controller so that we can more easily control certain loops here. Yeah? So you can still make a diagonal controller if you do the decoupling well and if you push certain modes such a way that they are not visible in the rigid body channels. This mode might not be that easy to control because it's a zero pole combination, so the phase is positive there. Another thing we are doing is to really go to model-based control. But if you do model-based control, all boils down to have a very good and accurate model. So we are now in a phase that we really want to push system ID techniques, control-oriented system identification, with the goal of applying robust control methods. So also the estimation of the uncertainty of the model is relevant. This is the work of Tom Ohme, and a number of PhD students working on that now. And our test beds are the systems of ASML. Apart from feedback, the most performance of ASML wafer scanners, 99.99%, is being made by feedforward. Acceleration feedforward, snap feedforward. With over-actuation, so having more actuators and sensors than rigid body modes, we go into a new era of manipulating feedforwards. And one of the things we are researching, and that's the work of Michael Ronde, he will also give a talk this afternoon, is to find out what kind of interesting matrix you can put in a feedforward path so as to not excite certain modes with your feedforward. And to really explore the freedom you now have in your inputs, because the dimension of that is higher than that of your rigid body modes. Just as an example, if you do input shaping, which is a sort of a standard trick for motion, you have a delayed set point. If you compare that to the original set point, of course you have a larger error, but in a minute you will see you don't have the excitations of the mode. With a mass feedforward you have a small error, but still you excite the modes, and with our new spatial input shaped feedforward we don't excite the modes. You can see that here in the frequency domain, where I plot the cumulative error spectrum. So from left to right you see the added content of the error in the frequency domain. In blue you see the input shaped one. You indeed see at a frequency of about 600 Hertz, you don't see anything more in the blue line, which means that indeed you don't excite the resonant mode there. The mass feedforward, the red line, indeed excites the flexibility at that frequency. And with spatial feedforward you can see that you don't excite the flexible mode. So you really explore the freedom in the dimension of your feedforward. So that's feedforward. We also work on using data, so data-based things. Because it's great to make models, but it's difficult. So maybe we shouldn't make models. So what we do here is to measure a frequency response. And for lightly damped systems, there is some theory from complex function theory that you can expand the frequency response into the Laplace domain. So you can make a 3D Bode plot, so to speak, so you can reconstruct h of s for a grid points of S in the Laplace domain. And from that we can in fact calculate closed loop pole locations over feedback parameters. So we can tune feedback parameters without having a parametric model, only having this data-based frequency response matrix, and we can calculate the closed loop poles. And we can then go for the maximum damping, for instance. Now this brings me to an idea what I got within Philips research, namely how to explore nonlinear things. And the following problem statement I put then down. Do there exist nonlinear feedback controllers that give a better performance for linear motion systems than linear solutions? Now obviously we all know that this will not be true if your specs and disturbances are modeled in a standard framework of norm-based control. But for instance, this Lewis servo from 1953 is already a very nice example. For a second order system, normally we take the proportional and differential gains constant. So you get a second order denominator polynomial. The damping, of course, is crucial for your fast response, but then you have overshoot. If you have a slow response, high damping, you don't have overshoot. Now if we can make the damping a function of the error, so if you have a large error you put low damping, if you have a small error you put high damping. In fact it's an LPV problem. In fact you have LPV type of things in the specifications now, not in your plant, not in your disturbances. You can make a very nice response for such a system. It's LPV application of the Lewis servo from 1953. The other idea is a span filter. I really like this idea. 1966. This is sort of the dream of beating the Bode sensitivity. So from the left side the error comes in. The top line is you rectify the error, you put it through a low pass. The bottom, the lower line is you have a sign function, so you throw away all magnitude information, you keep the phase information, you have a lead function. Then you multiply the two lines. And what you hope to get is a low pass with phase lead. Right? A low pass with phase lead. It works. This is the Bode plot of this nonlinear filter implemented and measured using a spectrum analyzer. This is the Bode plot of the band filter. Well, in fact, it's the describing function because you generate a lot of higher harmonics, right? But we have a low pass and phase lead. This is the dream of every control engineer, right? Now, does it work in practice? We applied it to a fourth order system, a mass spring damper mass. The solid line is a span filter. The dashed line is a tuned PD controller. So it works. It works. Nobody uses it, but it works. The key thing, of course, is if you have more noise, then the sine function blows up, you have higher harmonics, the whole thing goes down, right? So for specific disturbance conditions, this is really an interesting solution. Another question we made. Can we use frequency response functions for nonlinear systems? And we apply this for scanning electron microscopes. So they suffer from friction, especially they want to move really slow, nanometers per second, to scan samples. And you have stick-slip phenomena. Now what we did basically is we applied a sine as an input, and we took all the higher harmonics as output, and we tried to minimize that over the feed-forward friction compensation gain. So we tuned the friction feed-forward compensation so as to reduce all the higher harmonic content of the error. And that works really perfectly. So this is basically making use of nonlinear things, using frequency response functions and giving that back to the feed-forward tuning. Now then I went to the university and I started also to work on medical robotics because I thought, well, we are so good in motion control, ASML, CD players, etc. So let's do a few things on medical robotics. So this, you might know this picture, it's from Intuitive Surgical with the Da Vinci robot. But as a mechanical engineer looking at this, it's rather a large machine. Yeah? And second problem is that the surgeon, he does not feel any force. So we started a project making our own Da Vinci-like robot for the same application, but much smaller, much more compact, much more stiff designed, including force sensors in the mechanism, so we could give haptics back to the surgeon, in fact. We also worked on a new application for this type of robotics. That's the eye surgical robot we developed. So this is for operations at the backside of the eye, the retina. Very precise operations, and for a surgeon sometimes too difficult to really manipulate the instruments. So we managed to really design such a robot, including again force sensors, haptic feedback. Here you see how it works. So in one hand the surgeon can manipulate the slave robot, and at the left side he can use his own instrument. And he can then, together with the two hands, he can make an operation. And with the slave robot, of course, you can scale motion. So we measured the accuracy at the tip of this robot, and we achieved better than 10 microns, which is not possible for the surgeon. You see here, he's shaking. This is because it's my PhD student and not a surgeon, because they do a better job, of course. And then we also went to soccer playing robots. world champion for the first time. We were 4 years on a row in the finals, and we lost from Germany, which was the worst loss we made, of course, and from China 2 times, and from Iran. But this year we won. Next week, by the way, in Eindhoven, we are organizing the World Championships of this year. About 2,600 people worldwide are participating and coming to Eindhoven next week in all leagues, humanoid leagues, mid-size, small size. Really interesting. It's really high tech, and we also do that, of course, to prepare for the world which is coming up, where we have 2 less hands to help us if we are old. So we are developing care robots. And this is an interesting development where we try to add intelligence to such systems so that they can manipulate things, understand people. So this is twice the speed. It's still going slow, I think. So we are not there yet. This is our own hospital bed we have in our lab. They are also too expensive, these systems. So this is the great challenge, to make them really cheap, say 5K or so. This costs 100K. I mean, it's a prototype, but it's really a whole challenge to bring them down. Now, another subject I'm working on with my group is cars. Cars are becoming robots. So what's the difference between a car and a robot, right? So autonomous driving, electrical driving, hybrids. We think that cars are going to solve the problems. Yeah, they are going to be so smart. In a modern Mercedes-Benz, there are 100 million lines of software code. In a Boeing 747, there are 6 million. Right? So cars are becoming so complex that they need us. There are a lot of control problems, a lot of communication problems, a lot of software issues. I sometimes call cars an iPad on wheels. And I did that already before Tesla. Right? Going back 100 years, this is the car of my great-grandfather. He was also doing things in cars. He wrote 3 books on cars. This is one of the covers of his book. He presented that in 1920. And in the preface of his book, he states, well, steam machines are over. Electrical driving is sort of over. You know, most cars in those days were electric. And he wrote, well, the problem of electrical cars is the batteries are too heavy, the range is too small, and they are too expensive. 1920, he wrote this. And he moved on to ICEs, internal combustion engines. But 100 years later, this is going to be my car. So I will get it in August. That will be the first batch delivered in Europe. Dutch people are really happy with the Tesla. They ordered a lot. So I'm one of the happy people who can afford this also. And I'm going to get this Tesla. It's an amazing car. I call it a game changer. I call it a game changer because the whole setup of the car is so different than all the other cars we know. I think it's going to show that electrical driving is feasible in due time. It will take a long time before it actually goes into the larger market, but in all new technology there's a setup time, and we are at the start of that. So we are doing in my group a lot of work on hybrid powertrains, on energy management for DAF trucks, for instance, but also for passenger cars. We also work on continuous variable transmissions and on electrical driving. We also work on smart cars, of course. We all know the things about connected cars. You can in fact test a lot of the algorithms with robots. Here you can see a test with mobile robots. And if they simply look to each other with a simple LED device, you see that there is delay and that you get a traffic jam, basically. Right? You see a squeezing of the road. So if you now apply wireless communication, so they can really say to each other, I'm now braking or accelerating, then you see they all stop together. So this is of course already known for a long time. But actually we are doing tests now on the highway between Eindhoven and Helmond, where the automotive campus is located, in testing these systems. And I worked with a PhD student on this, proving string stability for heterogeneous platooning, etc. Autonomous driving will be also a major change in the automotive industry the next decade or so. All major car companies are working on that now. Volvo in Europe and Audi as well. So this is our famous highway. We do a lot of tests there together with TNO, really nice. I will skip this. So engines. So engines, they have had a huge development with respect to emissions and legislation. Now we are in Euro 6, so the top green part is now what is allowed in terms of particle matter, soot and NOx. And in fact, the truck manufacturers, they now develop their Euro 6 and they now say emissions is now no longer the problem. The key thing now will become fuel consumption, CO2. And for that, there are a lot of developments in hybridization of trucks, but also waste heat recovery systems to get energy back from the exhaust heat. And by that we are making more complex systems. And with that, we really need a lot of control people who are able to oversee all the interactions and can do dynamic modeling and optimization. So there's a huge challenge for us, for our field, to work on that as well the coming years. These are examples where we try to apply frequency response thinking, including getting a picture how nonlinear is our plant by making, by using the tools of, for instance, Johan Schoukens from Brussels in making the best linear approximation, but also quantitative measurement of how nonlinear is our plant. Now the last subject is nuclear fusion. I started with this about 6 years ago in my group. This is the picture of ITER, which is being built in the south of France, in Carandache. And if you look well at the left bottom, you see a person there. I hope you can see it. This is a huge challenge. If it's going to work, it's great. What is the key message with this project? Up to now, nuclear fusion is being done by people from physics and not people from control. Now they are building a huge thing. Now they see, hey, shit, we need control engineers. So what I like most the last 6 years is this debate with the physics guys. So I have in my group a part-time professor from physics, and the first time he was talking about diagnostics, I said, hey, what do you mean with diagnostics, man? What's that, diagnostics? And it appears that they are the sensors. But for them, diagnostics is you record, you go to your computer and you think and you analyze. People from physics, they analyze. People from control, they synthesize. And to do real-time things, you need real-time sensors. And there were many more of those words we could not understand really in between. But after 6 years, we really did a nice job. So for instance, we were one of the first really doing inline control of magnetic islands. So here you see a magnetic island in the plasma. We could measure it and actuate it. And the first question I had when I started with this also to the physics people is, okay, what's the process? The process, and they come up with a huge finite element program and said, no. What is the process the controller sees? So it's simple, one input, one output, what does the controller see? They could not say that to me. So together we developed a control-oriented model. Well, you recognize all these things, of course, if you apply control in a field where control is not yet used that much. Basically, you use the mirror, where you can shine the beam into the plasma, and you use the power of the beam to modulate it. And this is a simple plot where at 3.2 seconds or so, we switch on our controller. No, 3 seconds, sorry, we switch on our controller to reduce a magnetic island. And you can see in the bottom plot, which is an amplification of the top plot, that the magnetic island, which is sort of an oscillating thing, that is going to be smaller and smaller and smaller. Magnetic islands can distort the plasma and it can disrupt the whole thing. So it's key that you can control that. Another application of control is where we look to saw teeth. Those are instabilities in the plasma, sort of turbulence-related things. So you have a plasma here. This is a cross-section of the plasma, and you get a certain build-up of dynamics, and then certainly it's away again, and it's distorted. And we invented that by injection locking. So we just do open-loop perturbation with a constant frequency. You can sort of lock the plasma with your constant frequency. Quite interesting. So no feedback, just open loop injection locking. And the last thing I like as an example is that we now also have a PhD student for nuclear fusion using fission in the loop. And we learned all the things here from our soccer playing robots, and we apply that knowledge now for nuclear fusion. So we use cameras, optical cameras, to detect the edge of the plasma and to use that also real time for controlling the plasma. So quite nice as an application of fission. So to conclude, for me, high-tech systems are drivers for advanced control. Modeling is key also of disturbances and specs. Do more with data. We should love our experiments more than we sometimes seem to do. And my dream still is to beat Bode. Now to close up, I want to thank, of course, a lot of people. Not in the least Okko Boscha, who was my promoter, and he died away too soon, we think, just early this year. He passed away, unfortunately. And all the others listed here are members of my group or PhD students. And to really finalize the question, what happens if there is no feedback? Watch this video.
Whoa! 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 There you go. Oh, no, you go. Whoa! Oh, oh, shit. Oh, nee. Oh, what is that?
So, the main message is you really should like your work. Thank you.
Thank you, Martin, for an excellent talk. So we just have a couple gifts here.
Thank you.
Thank you for a token of our appreciation. It's just a couple ACC 13 mementos.
Okay, great. Thank you.
All right. Thank you.